Moving now to the second part, in which of course we know the concentration now of the permanganate, but we've got an unknown oxalate solution, and we're going to titrate again, but now we're going to use the volume of the permanganate with the known concentration of the permanganate to get moles of permanganate. Once we've got moles of permanganate, we can get moles of oxalate. Once we know moles of oxalate and the volume of the oxalate solution that contain that many moles, we can get the concentration. Now this is a much easier set of things to do the calculation for, because each time I'm starting off with the same volume of the unknown. So I can just go ahead right now, average these are all 10 by design, and now because each one of these corresponds to the same volume, I can average those together as well to get 15.29. You should never average until you're averaging apples and apples, so to speak. If I'd averaged in the part A the volume of the KMnO4 solution, I'd be averaging apples and oranges because those volumes corresponded to different masses of the oxalate. Here, because these volumes correspond to the same volume of the oxalate, I can just average all the one now and just do the one calculation. So how many moles of MnO4 minus did I have in this 15.29 cubic centimeters of solution, the average? Well, I knew that the volume of the permanganate, 0.0184 moles per cubic decimeter from part 1. There's the average volume, 0.01529 cubic decimeters, and I get 2.81 times 10 to the minus 4 moles. Convert that to moles of the oxalate. Well, we see again 5 oxalates need 2 permanganates, so the moles of oxalate must be bigger than the moles of permanganate. So I'll multiply the moles of permanganate now by 5 over 2, and I get 7.03 times 10 to the minus 4 moles. That, of course, was the average number of moles in these 10 cubic centimeters. So to get the concentration, take that average of the number of moles, 7.03 times 10 to the minus 4 moles, divide it by the 0.01 cubic decimeters, and my concentration is 0.0703 moles per cubic decimeter. And in this case, I did use all the data because none of these really look weird. You got 0.2, 0.2, 0.2, 0.3, 0.3, 0.4, 0.4. Finishing off with these post-lab questions, part 1 had to measure 10 cubic centimeters, 50 cubic centimeters of sulfuric acid and water with a measuring cylinder. Part 2, I measured 10.0 cubic centimeters of the oxalate solution with a pipette. What's the difference and why did I use the different glassware? Pipette is much more precise than measuring cylinders, so if you use it properly, you get a much more accurate measurement. Okay, pipette to do things accurately, measuring cylinders when you're just splashing it around, figuratively speaking. Part 1, we didn't really care whether it was, for example, 10, 9, 11, whatever of sulfuric acid, 48, 49, 52, and so on of the water, because this was just for catalysis purposes and a solvent. But what was absolutely important in part 1 was the mass of the ammonium oxalate, so I could get the moles. And of course the mass I did measure out nice and precisely on a 4 decimal place balance. Part 2, we want to know the moles of the oxalate, and the oxalate come from the solution, the unknown oxalate solution. So therefore I need to know the volume as precisely and accurately as possible, so I can know the moles as precisely and accurately as possible. Thus, in this case, measuring the volume nicely was very important because it directly related to the moles, which is what I needed for the calculation. Finally, already talked about this, concentration of unknown oxalate, 0.0703 moles per cubic decimeter, and I used all the data. Hopefully this answered any questions that you might have had about what I was looking for.